In this talk, I'm going to share with you our work on fast parallel indefinite integration with application to multi-compartment systems. This is joint work with Hunter Smith, a master's student at Texas A&M University, Central Texas. Talk summary. First, we'll talk about the indefinite integral and its application to multi-compartment systems. In the second part, we talk about the FFT method. We outline the method and we describe the implementation. The next section, we give numerical results. And in the final section, we draw conclusions and indicate future work. So, indefinite integral has the definition that you've seen in Calculus 1. I'm using capital H to denote the indefinite integral of little h. So notice capital H is a function of big T, which is the upper limit of the integral here. So I'm looking for a function of time, not just an individual value. Now, the calculation can be used to solve linear systems. Now, linear systems consist of compartments, and each compartment has a time-dependent evolution that's described usually by a box like this. This box denotes the following differential equation, that the rate of change of x is the contents or the population of this box, the rate of change of x over time is a of t, that's the input stream, minus r of t times x of t. R of t is the proportional rate of leaving. So you think of this in terms of population systems, epidemiology, in radioactive decay, and many systems have this sort of form, where you have an incoming flow and the outgoing rate is proportional to the population in the compartment. Now, A and R might depend on the contents of other compartments. In this case, you'd have a nonlinear system. So you can use this sort of methodology to describe nonlinear systems as well. Now, if you do have this isolated linear compartment, the solution is well known by using integrating factor. You can write it in terms of indefinite integrals. So if we had a good way of evaluating these indefinite integrals very quickly, we would have a fast way of calculating the solution for such a simple compartment in a linear multi-compartment system. All right, so again, relating the solution for a single compartment within a multi-compartment system to indefinite integral. And we're interested in methods for computing these indefinite integrals. So you have 3 indefinite integrals here that you would need to compute. Now, it's possible to compute indefinite integrals using FFT. I'm not going to say too much about FFT, just that it corresponds to a frequency decomposition you see on oscilloscope or spectrograph. And what a FFT does is it takes a sampled function on the interval 0 to t. So you can think of discrete samples where you take the value of the function h at equally spaced points and you generate coefficients. You generate frequency coefficients. Typically, you'll take 2 to the number of points will be 2 to the n. Here I have 2 to the k. So if you have 2 to the k points in your sample, so you're sampling the function at 2 to the k points, the FFT will have also 2 to the k frequency components, half negative, half positive. You can see the index here runs from minus n over 2 plus 1 up to n over 2. All right, so the FFT takes a sampled function at n sample points and generates n frequency coefficients, half positive and half negative. Now, once you have the FFT, you can take the IFFT also. The formula is very simple. You just change a positive to a negative and multiply by a different constant. And you can, using the FFT and the IFFT, you can actually interpolate the sampled function. If you sample a function at n points, then using the FFT, you can generate a continuous function of t that interpolates those n points and also is a very smooth function. So this formula is exact at the sampled times, but as I said, this will give you an interpolation of h in between those sample times. Now, so far I haven't talked about integral. I've just talked about how FFT can be used to interpolate a function. Now, How does FFT relate to integration? Well, to do an indefinite integral, all you have to do is take the FFT. These are the FFT coefficients at h sharp. Take the FFT coefficients and multiply each one by the correct constant, and then take the IFFT. This gives a three-stage method for finding a numerical indefinite integral. First, you take the FFT, then you multiply the FFT coefficients by the appropriate constants, and these are fixed constants, and then you take the IFFT. And there's also this term that relates to the zero coefficient in the IFFT, but you can deal with that similarly. All right, so those are my three steps. Now, why is this so great? Well, all these stages are parallelizable. This is the age of parallel processing. You have multi-core processors. You also have ways of using graphics cards to do parallel operations. So this is a massively parallelizable algorithm. In fact, an endpoint FFT or IFFT requires log base 2 of n stages, where each stage requires n over 2 parallel butterfly operations, and each butterfly operation requires 2 parallel complex multiply and add operations. So what does that mean? That means, for instance, if you have a 256-point FFT, log base 2 of 256 is 8. 8 stages. Each stage requires 2 parallel complex multiply and add operations. So theoretically, you could do a 256-point FFT in 8 times 2 processor cycles. If you have a completely parallelized implementation, you can do all those operations as parallel. You could do an 256-point FFT in 16 computational cycles. Now, there's some problems with FFT. The FFT essentially works on the periodic extension. So if you think of a function on an interval and then you repeat it, then you think about how when you repeat the function, you'll get something that's discontinuous at the endpoints. So when there are discontinuities, FFT experiences these wiggles. It's called Gibbs phenomenon. So it's not good to take the FFT, IFFT of a discontinuous function. You get these wiggles. So what we want to do is reduce these wiggles. And in our case, the wiggles are especially bad because they occur at the endpoints. And if you have error at the endpoints and you integrate, that error propagates throughout the entire interval. And if you iterate integration, that just compounds the problem. So we do want to get rid of this error at the endpoint. So this picture is showing the error in our integral estimation resulting from this Gibbs phenomenon. You can see how bad it is here. And the fact that it's so big here is because there are wiggles here. So we'd like to smooth the wiggles. Now, in fact, the Gibbs phenomenon doesn't occur if you have a smoothly periodic function. So if you start with a discontinuous function, try to find a function to add to it to get something that's smoothly periodic. Okay, that shouldn't be too difficult to do. Just adjust it. And I'll show you a picture in a minute. So h of t is the function that you want to integrate. G of t is a known function that you add to h of t to get a smoothly periodic function. So I can get the integral of h of t as integral of f of t minus integral of g of t. This integral has no Gibbs phenomenon. I can do this using FFT with little error. And if I choose a g of t with known integral, I can compute this by other methods without doing FFT. So this gives me an accurate indefinite integral for h. You can actually choose g of t to be a polynomial, which is easy to integrate. And you can integrate it exactly. So here I express h of t as a smooth function minus a polynomial function. So that gives me a good way to generate the indefinite integral of h of t without experiencing Gibbs phenomenon. So these are some details about how you would actually find this polynomial. Basically, you have the function on an interval. You approximate the function at the left and near the left endpoint by a polynomial, and you approximate the function near the right endpoint by the polynomial, and then you find another polynomial that when you add that to the original function, it matches up those two polynomials. It's really just algebra and rather straightforward. All right, so here's an example. This blue is my original function. It's a combination of exponential and sine wave. So that's what the blue is. And then you can see that I'm showing two periods of the blue. So my actual interval of interest is from 0 up to here. I think that's up to 128. So those are my interval of interest. And I've repeated the interval. So you see that when I repeat the function, I get a discontinuity. So if I take FFT of this and then IFFT, I'm going to get this Gibbs phenomenon. It's not good. So I want to add a function to this. Now the black curve is a polynomial on the interval from 0 to 128. And again, when I do the periodic extension of that, so here's the function, here's the repeat, it's not periodic. There's a jump here. However, if I add the two together, I get a function that is smoothly periodic. So what I'm going to do is I'm going to take the FFT version of the integral for the red function. I'm going to take the analytic integral of the dotted black function. I subtract and I get the indefinite integral of my original function. Right now, I can suppress the wiggles even further. I've suppressed them somewhat by doing FFT of a smooth function. But the wiggles are still there because, in fact, the nth derivative is discontinuous. So you still have a discontinuity. However, we know that the discontinuity produces wiggles at the endpoints. But I have an alternative expression for the indefinite integral at the endpoints. I do have these original polynomials that I used to generate the smoothing polynomial. So at the endpoints, I already have a method of integrating. So I just surgically remove the FFT integral at the endpoint and replace it with this other integral, and I reduce the wiggles further. So here's an example. This first shows the error without any correction, using the original function without trying to accommodate the discontinuity. So we get rather large errors like 0.05. Then I do this. If I add the smoothing function, do the stuff with g of t and obtain the f of t, and I do that, my error goes down to 10 to the minus 6. Now if I do this additional step where I replace the integral at the endpoint with the polynomial, I go down to basically down to 10 to the minus 8. So we're getting very good accuracy. And this was actually with a 128-point FFT. All right, so I mentioned that the FFT can be done in parallel. This is an illustration of the computations involved in computing an FFT. Here's your original data, and you notice that it's actually scrambled. This is x of 0 is here, x of 1 is here, x of 2 is here, x of 3 is here. That's one of the peculiarities of FFT. But if you put the data in the right order, and then you do these operations, this is 1, 2, 3, 4 stages for a 16-point FFT. Each one of these crosses represents a add and subtract. In this case, I'm adding these two. In this case, I'm subtracting this one from that one. So these are called butterflies. So you do the butterfly and then a complex multiply and then another butterfly. So you can consider that as a multiply and add operation. These are all, each one of these arrows is a multiply add operation that can be performed in parallel. And they're all complex, so they basically take 2 cycles. So if I count up the number of cycles for this FFT, if I can do it all in parallel, and I call parallel cycles, I just call them cycles. So theoretically, you could do an FFT in 2 times log base 2 of n parallel cycles. Now, when you're doing the FFT integration, following the FFT, you have to multiply each coefficient. Then you have to do the IFFT. So that gives you a total of 4 log base 2 of n plus 2 parallel cycles per indefinite integration. Now, this is without correction. So I'll give the corrected numbers in a moment. Now, compare this with conventional indefinite integral methods. You have Simpson's rule. You could actually do this. You could actually parallelize that implementation as well. But it's lower order. You'll see that with the same number of points, Simpson's rule is far less accurate. And it's not a generic operation. FFT is a generic operation that's used in many applications. But Simpson's rule is not something that's generic. Now, Romberg 4 is similar to Simpson's rule, only you do fourth order polynomial interpolation instead of second order, Romberg is actually a significant improvement over Simpson, but the same objections apply. It's still lower order and it's still not generic. Now, if you do spline integration, that's actually a lot worse because you're doing an n by n matrix multiply. So that's order of n operations at best. So spline is just not in the running. And you'll see that in the slide shortly. All right, this gives the total number of operations with the corrected correction for Gibbs phenomenon. And you have to add another 2L parallel cycles to take care of the smoothing and the edge effects. So, for instance, 128 point FFT in this case would be integration on 128 points would be 46 parallel cycles, would get you the indefinite integral for a function sampled on 128 points. All right, so in order to test out this result, we applied the algorithm to a parameterized set of exactly integrable functions because we want to see what the error is in the integral. So we recorded the mean execution time and log base 10 of the mean accuracy. And the functional form for these functions was exponential times cosine. So it has both oscillatory and sharply decreasing behavior. And this was our range of parameter values. So you both have oscillation and steep endpoints for these functions. And here's the results. Each one of these lines represents a different method. FFT is blue, Simpson, yellow, Romberg, red, the spline is green. You have execution time here, mean execution time in milliseconds, and you have log base 10 of the mean error this way. So down in this corner is good. You want small error and low execution time. So down in this corner is good. And you can see that Romberg is down in the corner. So for current implementation, Romberg wins by quite a bit. Notice some other things. The points on these graphs correspond to 128, 256, 512, 1024, and so on. So this point here is 128 point FFT. Now this takes longer than Romberg, but 128 point Romberg is up here. The error is about 100 times bigger. You have to go down to 256 FFT, 256 Romberg to compete with 128 point FFT. So this might be an issue in cases where it's costly to evaluate functions, to evaluate the function at different specific values. So you can see that as far as execution time and current implementation, Romberg is the best. We have this anomaly where, in fact, you have more points, you reduce the execution time. I think this is an anomaly of the MATLAB implementation. MATLAB tries to parallelize as much as possible. But you can see that Simpson also performs well, but as I said, lower order. You have to get, so this is 128, 256, 512, 1024. You have to get up to 1024 points to compete with the accuracy for FFT of 128 points. So you have to use you have to use 8 times as many points to get the same accuracy. With Romberg, it's only about twice as many points. Okay, so you have a trade-off here. In some respects, FFT is superior because you don't need as many points. And you also have this strange anomaly that 2048 FFT takes far less time than a 1024 FFT. And again, I think this is peculiarities of the MATLAB implementation. Okay. Now, of course, when you do numerical methods, you'll also have to estimate error. So I just want to say that with FFT, it's easy to estimate error because evaluating lower order FFTs is part of evaluating higher order FFTs. So you compute FFT on 128 points as part of the computation for the FFT of 256 points. So you can basically do it for 2 sampling rates at the same time and compare them, and that gives you an error estimate. So I haven't worked out the details, I just wanted to point that out. Now our idea was to apply this to a malaria model. Now each one of these compartments represents a population. This on the left, this is the host system, these are the humans, and this is the mosquito system, so these are the mosquitoes in various states. This S represents humans that are susceptible to infection. This I represents humans that are actually infected. And you can see that there's flow back and forth between these two compartments. This is the infection rate, and then this is the heal rate. And then you also have immigration and emigration, or death rate. You'll notice that this infection rate depends on this population here, which is the infected questing mosquitoes. So the mosquito population goes like this. You have susceptible mosquitoes who are questing, who are looking for a meal, and you have susceptible mosquitoes that are resting, and they go back and forth between questing and resting until there's some probability that the questing mosquito will bite an infected human. And then he will transition to the first exposed state, first exposed resting state. Now, this phi depends on the infected human population. So there's your nonlinearity, where the transition rate actually depends on the contents of another compartment. Okay. So all of these, so you can break this down into compartments. Each one of these compartments could be solved, if you know the input and the output, each one of these compartments could be solved by the integral expression I showed earlier. So this suggests using Picard iteration. For instance, I could start with a certain number of exposed mosquitoes, and from those exposed mosquitoes I can solve the integrals and find the populations of these compartments, which will also give me infected humans. Now, the infected humans are going to contribute more exposed mosquitoes, but I just don't add those yet to the system. I compute the additional exposed mosquitoes, and that gives me a correction to my initial population of exposed mosquitoes. So I rerun the system again with my initial amount plus the corrected amount, and I run through again, and I'll get a second correction, and so on. And this process should converge fairly rapidly. Now, without parallel processing, this is very costly because you have to find repeated solutions. But with parallel processing, each one of these compartment solutions takes only a few cycles. Now, there is a problem with this algorithm because the integrals required have very large dynamic range. When you take this exponential, the small value, you get small values up to very large values. You can have a 10 to the 30th range in values. So that makes the numerical computation impractical. So we're still researching methods of dealing with that. And conclusion. In conclusion, FFT is more accurate than other methods for a given number of sample points. And with current not fully parallelized MATLAB implementation, conventional methods, especially Romberg, are faster. FFT does have the potential of becoming a very fast method for indefinite integration once fully parallelized FFTs are implemented. And use of FFT to compute multi-compartment linear systems using Picard iteration is still under investigation. So thank you very much.